Today, on how it's made. Springs, the unsprung heroes of industrial machines. Pavers, we bring you a report from the street. And pianos. We'll lift the lid on the making of a grand piano in a special two-part report. A spring is a flexible metal device that returns to its original shape or position after it's stretched, squeezed, or twisted. Springs were first used in clocks during the 16th century, and starting in the late 1800s, in chair seats and bedding. Today, springs pop up all over. They're crucial components of modern technology. Different types of springs include compression on the right and extension on the left. During use, these torsion springs will twist at one or both ends. Workers start with rolls of steel cord. The cord diameters range in size depending on the type of springs being made. A machine called a de-reeler unwinds the roll, feeding it to a computer-guided forming machine. This forming machine forces the cord through a channel, shapes it into a coil, and then cuts it into segments. Small wheels and a metal shaft guide the cord into shape. These are torsion springs for use in the automotive industry, which relies heavily on a variety of springs. The average car, for example, has about 350 of them. A cone-shaped yellow sensor detects the correct angle of each spring. A good reading is required, so the machine can move the next spring forward through the channel to be formed. This machine can produce up to 2,000 springs per hour, depending on their size. Here, another larger forming machine creates extension springs that are nearly 16 centimeters long. A mechanical arm grabs the coil and chops it into segments after it's formed in a channel. As the coil emerges, another mechanical arm steadies it to prevent it from vibrating. This keeps the spring's tension constant, enabling the machine to produce at top speed. In slow motion, you can see how the machine grabs the coil's first ring and bends it to form a hook. This all takes place as the coil emerges from the channel. A vise then secures the last ring on the end of the coil, while another arm twists it to make the spring's other hook. Slowed down, you see how two arms surround the coil being held in the vise. One arm then grabs the last ring, while the other arm twists it upward. This machine makes compression springs, a model with tapered ends that's often used in seat belts. A metal probe detects the correct length of the springs after they're formed. The machine has 4 rotary shafts called cams. A computer ensures each spring has the desired specs. The springs are also heated to relax the metal. This gives them the ability to retain their shape after flexing. Another machine creates longer, thicker torsion springs. It shapes the cord into a coil with a shaft and then passes it over a tube to steady it. This ensures the spring will have the required tension. Springs can be as thin as human hair or as thick as a broom handle. Train wheels, for instance, include some of the industry's thickest compression springs. This machine makes another type of spring, often called wire forms. They're flexible steel cords curved or bent at an angle. These ones, shaped like a W, are used in ovens. Here, a worker places a spring into a machine that makes its hooks. He uses an adapter to avoid hurting his fingers. He places each one individually because specs for springs can vary by minute amounts. This company makes some springs with hooks made of 2 rings instead of 1. Clients order them this way because the hooks are more durable. Custom orders for springs can range from just a few to many thousand. This is another type of wire form. It'll be used in a firearm. A worker assembles it by hand because it's so intricate. After joining 2 base pieces, he places them into a small die. Using a foot pedal, he controls the die to bend the segments and complete the assembly. To check the compression spring's tension, a worker tests it with a weight gauge. The correct tension varies depending on what the client wants. A 3.8 centimeter long spring, for example, might need to withstand 5 pounds of tension when compressed to 2.5 centimeters. To test an extension spring, workers just add hooks to the weight gauge. Whether they're extension, compression, torsion, or wire form, and whether they're inside pens or satellites, springs prove that some old ideas definitely still work. You could say that interlocking concrete pavers came out of the rubble of World War II. In post-war Holland, there weren't enough clay pavers to rebuild city streets, so the Dutch began making concrete pavers. The Germans refined the technology and exported it to North America, where they found a quick road to success. Call it a concrete solution for paving. These pavers are solid, and the interlocking design disperses weight, easing the load on the road. To make these pavers, a conveyor belt delivers concrete sand to a weigh belt that weighs the coarse sand as it falls onto it. The weigh belt carries the sand forward, while another conveyor belt unloads stone chips to be weighed. These chips are no larger than 1/3 of a centimeter. The ratio of sand to stone chips varies, depending on the type of paver being made. The weigh belt transports the stone chips forward, along with the coarse sand. Both are en route to the skip hoist. They spill off the conveyor into the skip hoist, which is essentially a bucket on rails. Cables pull the loaded bucket upwards. It stops about 9 meters up, just above a big concrete mixer. A trapdoor opens and dumps the sand and stone chips into the mixer. 6 giant steel paddles mix and then rotate and mix again, while cement is added automatically through several nozzles on the side of this enormous mixing bowl. Making pavers is a bit like baking cookies. Too much or too little liquid in the batter, and it won't bake properly. Water is added until the consistency is just right. Nozzles also shoot a pigment into the mix to tint it. The mixture looks dry and crumbly, but the recipe gives it just enough moisture to form the concrete. Now a filling wagon spreads the mix over a steel mold containing up to 50 paver-shaped cavities. The mold press head applies 10 tons of vibrating pressure. This pulsating force compacts the mixture into the paver mold and removes any air pockets, which could weaken the pavers. Hydraulic cylinders lift the mold, leaving the pavers on the press board. The press board slides out, and the mold once again gets filled in and makes another 50 paver stones. It only takes about 10 seconds to mold, compact, and release a batch of pavers. The press boards filled with pavers slide into a rack. A hydraulic chain hoist lifts each board into a large holding rack. There, a special moving wagon called a finger wagon picks up all the boards from the rack in just one move. The electrical wagon moves along a rail to a curing kiln, where it's almost 38 degrees Celsius. The pavers actually generate the heat due to a chemical reaction from the combination of cement and water. About 12 hours later, the finger wagon carts the pavers out of the kiln. They're now 70% cured as a result of the chemical process that binds the cement, sand, and gravel, causing the pavers to harden. The rest of the curing will happen over the next 28 days. The pavers are now sturdy enough to handle, so 4 steel arms with rubber pads move in and straighten the stones on the board. These alignment arms are hydraulically driven. They arrange the concrete pavers so they interlock snugly. Now, hydraulic clamp arms lift the pavers off the board and begin to pile them up. They're making a cube of stone. This stacking machine is called a cuber. It packs 9 or 10 layers of pavers on top of one another to make this cube. The cube is actually called a bundle. It will be strapped and shipped out to the job site. These concrete pavers will be on the road soon, in more ways than one. We still say tickle the ivories, even though ivory isn't used to make piano keys anymore. It's banned to protect elephants who were killed for their ivory tusks. Pianists now tickle the plastic. But the techniques involved in manufacturing a piano haven't changed much and still rely on hand craftsmanship, just like a century ago. Beautiful music is a triumph, but so is the piano itself. Made of inner and outer rims, a soundboard, treble and bass bridges over which the strings are stretched, and a heavy cast iron plate. To make a piano rim, automated rollers spread glue onto sheets of hard rock maple, coating both sides. Then they layer the glue-soaked sheets 5 to 8 deep, depending on the model of the piano. Workers feed the wet layers of wood to a rim press. An impact wrench, powered by compressed air, turns the clamp screws. The screws bend the wood into a piano rim form. They measure the pressure on the layers with a torque wrench. Steel arms reach across the wood, holding the shape while the glue dries. After 24 hours, workers loosen the machine's grip, and the rim now holds its contour. Now it's into what's called the conditioning room for more drying out. The piano rims stay in this warm, arid room for 30 days. It's time to make the bracing structure. They place glued struts inside the rim, then apply pressure with a clamp. The framework remains in this embrace for an hour while the glue dries. This piano will also have a tension resonator for extra support. Steel turnbuckles attached to a center hub. A worker tightens the turnbuckles with a wrench. Then he thumps it to make sure it's tight and won't rattle. Next, they'll install the soundboard made of spruce and the 2 bridges. Strings will straddle the bridges and transmit vibrations to the soundboard, which is the amplifier of the piano. A worker glues ribs onto the soundboard. He lowers wooden clamps over each rib to apply pressure while the glue dries. That takes about an hour. Next, he thins the ribs around the edges with an automated stagger tooth shaper cutter. This will allow the soundboard to resonate freely when the piano is played. Now they position the soundboard in a bridge press. Then they place a bridge locating fixture on top of the soundboard. This device holds the bridge in place while it's glued to the soundboard. After the 2 bridges are glued down, they lower the soundboard onto the piano rim. They hoist a cast iron plate onto it. It's a critical fitting. If they don't get it right, the piano will never function properly. Then the plate is removed for finishing. A worker cuts notches in the bridges, which are now topped with a lubricant. This very sharp chisel cuts through the hard maple like butter. Each notch will cradle 3 piano strings, giving them the freedom to vibrate. Now they roll glue onto the outside case of the piano, which is made of rosewood veneer on maple. They fit it snugly over the rim structure. A mechanical clamp holds it in place for an hour while it dries. Then they stand the entire piano on its side. spinning cutters shape the arms that sit next to the keyboard into an elegant curve. This is called a vertical stroke sander. A worker runs it along the side of the piano to smooth out the wood. After a black polyester paint is applied, they buff it up with this electrical cloth polisher. Then they hand rub a mirror glaze cream into it until you really can see yourself in this half-finished piano. Raw talent and deep pockets. That's what a budding pianist needs initially, because a grand piano can cost about the same as a luxury car. And, like a luxury car, when you lift the top of a grand piano, you'll see that a lot has gone into its construction. The bass and treble bridges are now fixed to the soundboard of this half-finished piano. To add glamour, they spray gold paint on the cast iron plate. The next step involves the pin block, which holds all the stress. It bears 45,000 pounds of tension from the strings and transfers it to the iron plate. He drills into the maple pin block through holes in the iron plate over it. The holes are for the tuning pins, hence the name pin block. They unfurl pieces of steel wire from big coils. Using a vice grip, the worker twists the end of the wire into a neat loop. Then he hooks it onto a hitch pin on the back side of one of the bridges, making sure it runs between the guide posts over the bridge. Now he threads the wires through another guide, called an agraffe. Using wire cutters, he snips the wire to the exact length that he needs. Then he wraps the wire on a tuning pin, using a device called a stringing crank. He taps it into a hole in the pin block. Then, using a pneumatic hammer, he drives the tuning pins into the pin block. Now the string stretches from above the bridge to the pin block. Each string is under a tension of up to 425 pounds. Again, a force that will be kept in check by that heavy cast iron plate. Now he places little felt-covered blocks called dampers above the strings to stop them from vibrating when a note is played. Using pliers, he makes parallel bends in the damper wires so they're aligned. He pounds the keyframe, checking for gaps that could cause knocks under a pianist's vigorous blows. He smooths out the gaps, shaving off bits of wood with a strip of sandpaper attached to a handle. Now another worker presses the piano keys in between steel guide pins that have been installed in rows on the keyframe. She uses an air cylinder to push the back check into the end of a piano key. The back check is a piece of wood covered with felt and buckskin that will catch the piano's hammer after it strikes a string. It's time to make those hammers. She glues the felt-covered top onto a thin piece of hornbeam, a species of very strong wood. When a pianist hits a key, it will catapult the hammer into the string, and that produces a note. Now she aligns the hammers to be perfectly parallel, using a plastic square as a guide. This is called squaring it up. Next, she sands the tail of each hammer with a file, so there'll be no sharp edges to damage the back check. Then she attaches the hammers to the top of the keyboard with screws. Now she places weights on each key and then gently taps the rail to get the hammers moving. She's testing the amount of effort it would take for a pianist to push each key down. This is called the weigh-off. After she determines how much weight is needed, she marks a place on the side of the key and drills 1 or 2 holes. She plugs each hole with a piece of lead. In a process called swedging, she pushes a divot into the lead so it expands and fits snugly into the key. The lead will counterbalance the weight of the hammers and give the key the required amount of weight. Next, this technician checks each hammer and each key, making subtle mechanical adjustments so they move smoothly and fluidly. It's the piano's first big tune-up. He fine-tunes the hammer action by using a let-off tool to adjust the driving mechanism. The piano is now ready for the hands of a skilled pianist and the ears of an appreciative audience. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.